Hello everyone. Today we are going to look at the resonance and power in AC circuits, and we will lecture in this lesson. The objective for this lesson is you are going to be able to deduce that the mean power in a resistive load is half the maximum power for an alternating current. Let's start with the resonance. We have an RLC circuit like this, and now the power of the circuit, the voltage of the circuit or electromotive force of the circuit is going to change with E is equal to E max cosine WT. If we keep every element, I mean R, L and C constant, but change the frequency of the source, how the current in the circuit is going to be affected. Now as you see here, I have a graph. The current is going to be affected like this. Initially we will have minimum current, then it will increase to a maximum value, and then it is going to decrease. So why, when we change the frequency of the source, the current in the circuit is changing like this? Remember that the impedance of the circuit is equal to R squared WL minus 1 over WC. So as we change this angular frequency, the reactance, the inductive reactance and the capacitive reactance both are changing. So as these two values are changing, the Z is changing. We know that the current in the circuit, I is equal to the voltage divided by Z. So as the impedance of the circuit is changing, the current in the circuit is also going to change. Now look at this inductive reactance and capacitive reactance. At low frequencies, this is going to be small and this is going to be high. As I increase W, this will increase and this will decrease. At a certain frequency, these two are going to be equal to each other. WL will be equal to 1 over WC. At the instant when these two reactants are equal to each other, they are going to vanish and they are going to cancel each other. The impedance of the circuit will be equal to Z will be equal to R only, and it will be minimum. And when this Z is minimum, current will be maximum. So as we increase the frequency, this is the change of the angular frequency, the current in the circuit will increase and it will get a maximum value at a certain frequency, and we call it the resonant frequency. And then if we continue increasing this angular frequency, the current is going to decrease again. Why? Because this value, these two values are going to cancel each other only and only at W0. At this angular frequency, both are going to cancel each other and Z will be minimum and current will be maximum. We call this frequency as angular resonant frequency. So when these two are equal to each other, from here resonant frequency W will be equal to 1 over LC square root. This is the angular frequency, but only in terms of the frequency, it will be F is going to be equal to 1 over 2 pi LC. Okay, and at the angular frequency, since these two are equal to each other and they are going to cancel each other, only the resistor is effective. And remember, when there is only resistor in the circuit, the voltage change and the current change are going to be in phase. There is going to be no phase difference between them. Let's look at the power in AC circuits. In such an AC circuit, the power loss is going to be associated only with the resistor. No current loss, no power loss will occur in inductor and in capacitor. As the voltage of the source changes with the time, the voltage is changing with the time, the capacitor and the inductor both are going to store the energy and then they are going to release their energies. This capacitor is going to be charged and discharged, and the energy is going to be stored in it. Similarly, the energy is going to be stored in the inductor, and then this energy is going to be delivered to the circuit again. So momentarily there is going to be some power, some energy stored in these two elements, but then they release their energy to the circuit again and they do not dissipate any energy. Only energy is dissipated in the resistor in an AC circuit. So we know that the current in an AC circuit is having such a change. The graph is something like this. The instantaneous power loss in the resistor, remember from the DC current, power is equal to I square R. Similarly, in alternating current circuit, again power is equal to I square R. But in this case, the current has a changing nature. It is changing, and we know that the current is changing with I is equal to I max cosine WT, and power is I square R. So if we take the square of this function, we will get I max square cosine square WT times R. This is the power associated with the resistor in the circuit. If we take the square of this function, it is going to be something like this. All zeros are going to be positive now, since we are squaring. This is going to be the change of the power in the circuit, in the resistor, and it is I square R. But as you see, it is also changing. Okay, it has maximum value, minimum value, and so on and so forth. But we need an average value for the power in the circuit. The average value will be the half of this changing, so it will be, the maximum value is I max, this is max, I max square R, and half of it is going to be the average power in the resistor. So the average power in the resistor is going to be formulated like this. So P average will be equal to 1 over 2 I max square times R. We can also express the power in terms of RMS current and RMS voltage. We know that the RMS current is equal to maximum current divided by square root of 2. Let me write it. I RMS is equal to I max divided by square root of 2. Similarly, V RMS, remember from our previous lessons, is equal to V max divided by square root of 2 again. So if we express the power loss in the resistor in terms of RMS quantities, the power is going to be I RMS square times R. And it's also equal to V RMS square divided by R, or I RMS times V RMS. So we can find the power in terms of RMS square times R, or power is equal to V RMS square divided by R, or power is equal to I RMS times V RMS. And the power, the average power supplied by the electromotive force, I mean the average power of the source, we are going to calculate it with this formula. I'm not going to be interested in the derivation of the formulas, but please note that the power of the source will be calculated by I RMS times E RMS times cosine phi, and this cosine phi is called power factor. This comes from the fact that the current and the voltage in the circuit is always changing, and that's why the P max for the source will be equal to I RMS times E RMS. But instantaneous value, to get the instantaneous value, if they are not in phase, I mean if the current and the voltage are not in phase, then we need to multiply with the cosine of the phi to find the power of the source. Let's continue with some examples. The first example is what is the resonant frequency for an RLC circuit with R12, L 5 millihenry, C is 5 microfarad, and B, if an AC source of amplitude 10 volt is set to this frequency, what is the average power transferred to the circuit? Let's first find the resonant frequency. We know that resonant frequency F is equal to 1 over 2 pi square root of LC. And now let's plug in every term here, and L is equal to 5 millihenry, 5 times 10 to the negative 3, and C is 5 times 10 to the negative 6, it's microfarad, and in doing this calculation we are going to get approximately 101 Hertz. This is going to be the resonant frequency. B, what is the average power transferred to the circuit? So to find the average power to the circuit, we remember from our formulas, P average is equal to, we are going to use V RMS squared divided by R. But to find the V RMS, we need to write V RMS is equal to V max divided by square root of 2. Remember, these were explained in our previous videos. Here is the amplitude is 10 volt. It means maximum value of the voltage is 10 volt. So it will be 10 over square root of 2. So average power will be equal to the square of this one, and divide by 12 is the resistor, is given 12 ohms. And in doing this calculation, we will find 4.2 watt approximately. Next, the resonant frequency of an RLC circuit is 1000 Hz. If the self-inductance in the circuit is 10 millihenry, what is the capacitance in the circuit? We know that F is equal to 1 over 2 pi LC. This is the formula for the resonant frequency. In rearranging this formula, we can find an expression for the capacitance. It will be 1 over 4 pi square F square times L. So let's write every term, then we will get 1 over 4 pi square, and F is 1000 Hertz square, and the inductor is 10 millihenry, 10 times 10 to the negative 3. So if we calculate, we are going to find approximately 2.5 microfarad. So next question, for an RLC circuit, R is equal to 200 ohms, L 100 millihenry, and capacitance is 10 microfarad. At what frequency is maximum power dissipated in the resistor? The maximum power dissipated in the resistor occur in the resonant frequency. It means we are going to find the resonance frequency. Just find the resonance frequency. It is 1 over 2 pi LC squared. So if we plug in the givens, we will get 2 pi square root of the L is 100 millihenry, 100 times 10 to the negative 3, and capacitance is 10 times 10 to the negative 6. So if we calculate it, we will get approximately 159 Hertz. At this frequency, the power dissipated will be maximum. This is the last question. A series RLC circuit consisting of 10 ohm resistor, 50 microfarad capacitor, and 2 millihenry inductor. The output voltage of the source is 66 ERMS. This is the RMS value of the voltage at 400 Hertz. What power is delivered to the resistor? The power delivered by the source, P source, you can see our previous slides. P source is equal to I RMS times V RMS times cosine phi. So here we only know V RMS. It is 66, but we don't know I RMS and we don't know cosine phi. To find I RMS, we need to find the impedance of the circuit. I RMS is equal to E RMS divided by Z. So to find the impedance, we need to first know the capacitive reactance and inductive reactance. So the capacitive reactance XC will be equal to 1 over 2 pi FC, and it will be equal to 1 over 2 pi. F is 400 times C is 150 farad, 150 times 10 to the negative 6. So in calculating, we will get 0.27 ohm for the capacitive reactance. For the inductive reactance, XL is equal to 2 pi FL, and it will be equal to 2 pi, 400 is the frequency, times L is equal to 2 times 10 to the negative 3. Here is the 2 millihenry. So in doing these calculations, we will get approximately 11 ohms. Then now, not 11 ohms, it will be 5 ohm. This will be 5 ohms. The Z in this case, we know the impedance, Z is equal to R square, it is 10 square, R is equal to 10 ohms, it's here, plus XL is 5 square, 5 minus the XC, it is 0.27 squared. So calculating this one will give us 11 ohms, approximately 11 ohms. Then now we know the Z, we can calculate I RMS. It will be equal to, E was equal to 66 divided by Z is 11. It will be 6 ampere. This is the I RMS. Now we know I RMS, we know V RMS. We need to find the cosine phi. Cosine phi, remember again from our previous calculations, was equal to R over Z. This comes from this diagram. This is R, and here is the XL minus XC, and this is Z. So this is the phi. Cosine phi R over Z. We know R is equal to 10 and Z is equal to 11. It will give us approximately 0.9091. So now once we know every term, we know cosine phi and we know IRMS, VRMS, we now can calculate the power delivered by the source. P will be equal to IRMS is equal to 6, VRMS is equal to 66 times cosine phi is 0.91. This will give us 360 watt. This is A. For B, what is the maximum power the source can deliver? The maximum power, for the maximum power, P max, in the case of maximum power, the cosine phi should be equal to 1. Then we are going to only multiply RMS and VRMS. So IRMS was 6, the other one was 66. So it will give us 396 watts. Finally, how would the capacitor have to be changed for this to happen? For the maximum power, the XL and XC, I mean the capacitive and inductive reactances, should be equal to each other. So then we can write XL must be equal to XC, and we know that XL is equal to XL was equal to 5 ohm. And then if they are equal to 5 ohm, what should be the value of the capacitance so that its capacitive reactance is also 5 ohms. Remember that for the capacitance we can write 1 over 4 pi square F square times L. Now let's plug in every term. It will be 4 pi square F was equal to 400 square times L was 2 times 10 to the negative 3. In calculating, we are going to find 0.8 microfarad. So if we change the capacitance of the capacitor to 0.5 microfarad, then we are going to get the maximum power in the circuit. That's it. Thank you for listening.